So we're going to look at a conducting sphere that's put inside of a uniform electric field. So just go through this a little bit more. So here's our electric field. I'll go ahead and put the arrowheads on them. Okay, and what's going to happen is the field is going to affect these field lines. As we know, for example, that electric field lines are going to be perpendicular at the surface of a conducting object. So basically we'll distort this field. So you'll get a superposition of the uniform electric field that you start off with, as well as the field caused by the charge configuration of this conducting sphere. As the charges move around on the sphere as influenced by the external field, they kind of create their own contribution to the field. So this is what we want to solve. So since it's a conducting sphere, none of this information is going to reach inside of it. The charges will move around and cancel out the field. So inside, there's no field, right? So we'll go ahead and set the surface to 0, of a potential of 0, electric potential, right? All right, and this is also true of the surface of the sphere. So anywhere from small r less than or equal to big R, which is the radius of the sphere, the potential will be 0. All right. Now, if we look very, very far away, we have a uniform electric field. And if we're putting this into sort of cylindrical coordinates, since we have azimuthal symmetry here, we're going to have basically, I'll write this over here. So the E far away, so this E is going to equal basically the minus potential out here, say at infinity or whatever, multiplied by Z, right? Because, no, I did this wrong. Divided by Z, right? The electric field is volts per meter. Derp. Okay, so V equals minus this field vector multiplied by Z. So we're just going to put in the Z into spherical coordinates and call this minus E Z cosine. And I guess I should make this, right, potential is not a vector, it's a scalar, so this would be like a dot product, so we can get rid of the vectors. Okay, so we'll go ahead and put a 0 on the subscript on there so we don't get confused with the electric field in general. All right. Okay. All right. So at very large R, V is going to be equal to this down here. All right. Okay. Now we will go to our general solution, Laplace's equation, for cylindrical symmetry. Use n for the subscript. A sub n times r to the n plus b sub n divided by r to the n plus 1. And this is all, oops. So then we have our Legendre polynomial of cosine of theta. All right. So we'll start with inside, and basically at the surface, right? This all has to go to 0. So this part's not going to be 0, but we can get 0 from these coefficients. So at this little r equals big R, so at the surface of our sphere, we're going to have a sub n big R to the n plus b sub n over big R to the n plus 1 equal to 0. All right. So when we'll just go ahead and use this to get rid of one of our coefficients, a sub n or b sub n. We'll go ahead and solve for b sub n. So we're going to subtract this minus a sub n r n. Okay, and then we would still have this big R to the n plus 1 down here, but we're going to multiply it and bring it over here. Okay, so now we'll work on our second boundary condition here out at very large R. All right, so for this, we'll put a little infinity down here to remind us what we're looking at. Okay, so we have an a sub n to the r multiplied by r to the n, like this. All right, now we're going to go ahead and plug in what we found for b sub n right here. So that's a minus a sub n r. This is a big R to the 2n plus 1, and this is still divided by little r to the n plus 1. Okay, and here we have our Legendre polynomial. Okay, so now this whole mess here is going to have to be equal to is our boundary condition out at r equals infinity, which is this minus big E naught r cosine theta. So we're going to go ahead and start writing this out just to illustrate this. So we're going to start with n equals 0. So we have, first of all, we can factor out an a 0. Well, what the heck, we'll leave it in for now. Okay, so r to the little n, r to the 0 is 1, okay, minus, here we have an a sub 0 big R to the 2n plus 1 over, which 2 times 0 plus 1 is just 1, right? So this can just go away. And here we have a little r to the 0 plus 1, which is just r. And these are multiplied by the first Legendre polynomial, which is just 1, right? So we don't even have to write it. Okay. Now let's go ahead and do our 1, our n equals 1 terms. Okay, this is an r to the 1. Alright, now this time we get a big R. 2 plus 1 is 3. And on the bottom we have a 1 plus 1, which is r, which gives us r squared. Alright, but these terms, I'm going to go ahead and write it like this, are multiplied by when L equals, oh, I wrote an L here. Oopsies, we're using N. When N equals 1, our Legendre polynomial just goes to whatever is inside here. So P1 of x is just x. So P1 of cosine is just cosine. All right. And for fun, we're going to go ahead and write our next term. And this is for n equals 2 r squared minus a2 r to the 5th. 2n plus 1, 2 times 2 is 4 plus 1 is 5. And then 2 plus 1 is 3, so we have an r to the 3rd on the bottom. Okay, and then our Legendre polynomial gets a little crazier. We have a 3 halves cosine squared of theta minus a 1 half. Alright, we can just go on and on and on and on with this. But what we're looking for is we're looking to match this condition right here. Alright, so I'm going to go ahead and write that down here in this bottom corner. Okay, so the key here is these higher and higher terms of our Legendre polynomials. We may get some terms that have just 1 power of cosine in them, but they also come with extra baggage. So basically, and you can use orthogonality or whatever, but we're not going to be able to get any other combination of these Legendre polynomials that will give us just 1 cosine, except for this one right here. So, and this, we don't have to worry about like these terms with r on the bottom because they will all go to 0 at infinity anyway, right? So we basically, these are all, right, at r equals infinity. This goes to 0, this goes to 0, this goes to 0, right? So we're really looking at these ones here. And basically what we end up with is only, all we need to match this is this right here. And if you think about this in terms of, just how many, if we were to, we're trying to describe kind of a simple field, so we shouldn't need a bunch of higher order terms to describe a simple field, right? It's just sort of like a dipole field that we'll show in a bit, right? So we don't need a bunch of higher, higher terms. So let's just pick out the one that we want. And again, I mean, we could keep this term here too, but all this is a constant, and with potential, you can set a constant pretty much anywhere. We're setting this to 0 because we set the potential at the sphere. We're calling that our 0. So, but you can add a constant potential to any of this, and so this is just kind of extra. Right? Okay, so we have an A1R. So again, this is the only term that survives. I won't write this one here because it goes to 0 at infinity, right? Cosine of theta, and it's equal to minus E naught R cosine of theta. So what we get is an A1 is equal to just this minus E naught. All right. Now, if we look back to where we solved for our B1s in terms of our B's in terms of our A's, we can also get B1. And again, because all of the other A's are going to 0, all the other B's are going to 0 too. So all we need is a B1. So this right here, we have these. So we're basically plugging a minus E naught right into here. The minus signs will go away. E naught big R, and then we have n is 1, so we have a cubed here. Okay? All right, so now let's write our potential in general. So we started with this big ugly sum right here, and only, well, I guess we started with this one here, which had B's and A's in it, and then we worked it down to this one, and now we just end up with this one term, or one n, right? So what we get is, I'm going to go back to our first version since we had this. All right, so we're only doing with n equals 1. So here we have a minus E naught R, okay, R to and R to the 1, okay, and then we're going to add our B1 here, and then this is R to the 1 plus 1, so little r squared. All right, and then I wrote this with an L, used to writing L's. This is also a 1 here, so we just have a cosine of theta. Okay, so I believe this is all fine and dandy. So if you're following along in Griffith's, what example is this? This is example 3.8. We'll get into crazier stuff too. But so now let's go ahead and calculate the surface charge density on our conducting sphere. Like this. All right. So we have our minus epsilon naught out here, and let's see what we get. So we have a minus E naught right here, and then a minus, so we're taking the derivative with respect to little r, which is r to the minus 2, so we're going to bring a minus 2 out front, and then this changes to an r cubed on the bottom. So big R cubed on the top, little r cubed on the bottom, and cosine there. All right, but again, this is evaluated at little r equals big R, so save time, we'll just write that right here, okay? So these are going to divide out. All right, we'll deal with the minus sign right here. This, we just have a minus 3, big E naught, right? Uniform electric field magnitude. And then these minus signs are going to go away. So we had a 3 epsilon naught big E naught cosine of theta for our charge density. So if we go maybe one step further than Griffiths, and let's ask ourselves about the dipole moment of this sphere. So if we look at, this is equation 3.99 in Griffiths, if you're following along in Griffiths. The potential of a dipole, put our jar in there, 1 over 4 pi epsilon naught. Okay, and we have our dipole moment, unit vector, kind of like this, right? So if we go back and look at the potential that we found, so potential, whatever, I'll just use the same thing here. All right, this time I'm going to split it up. So all right. All right. So we're splitting up. This is the total potential outside of our conducting sphere. And we know we have a uniform electric field out on the outside, right? And looky here. This is from our applied electric field. I'll just say applied potential. Alright, it's just what was already there before we put our sphere in there. And then we have this term right here. So what we're going to do is compare this term here, which is just from the charge configuration of the sphere, and we're going to compare it to the potential due to a dipole at the origin right here, and we're going to find our little dipole moment for our sphere. So let's write this up here. So 1 over 4 pi epsilon naught. So what we end up with, we could write this as a p dot r without the hat, and then make this a 3 on the bottom, right? Just the vector without the hat divided by its magnitude is our hat. So and this p dot r is going to be a pr cosine, just using the z-axis as our, just like we did with the external field, and then we still have our r3 on the end. All right, and this r on top will divide out with one of these, and we'll go back to having an r squared. So maybe that's a long way of doing it, but all right. So if we look at this little mess here, we have some common terms. We have a cosine theta, we have a little r squared, and what's left over I will put down here in an equation. So we have a little p 4 pi epsilon naught, and what we have over here, E naught r cubed. All right. So this tells us that our, let's see if we can squeeze this onto the bottom of this paper. Dipole moment of our sphere is equal to 4 pi epsilon naught big E naught big R cubed. All right, and what direction is it in? It's just in the z direction, because the dipole moment goes from the negative charge to the positive charge. So just like this, same direction as the as the field. So, right, yeah, as this external field. So, if we stick it in a Cartesian coordinate system, or I guess cylindrical, right? It's just in the z-hat